All right. Welcome to a special lecture on vector norms. So, for this lecture, we're gonna focus on these things, functions specifically called norms. Well, previously we have already talked about these query functions, where it's basically just a function. Instead of the traditional way which we look at functions, we see functions as a way of extracting information from some kind of data, right? So we have seen like Q1 was how do you get the maximum value, max of X, like, or getting the minimum value. So these are essentially just functions that give you interesting information about the vector. Now, today, we're going to learn like a very, very special function, query function, that extracts very important information about the vector. And this function is called a norm. Okay. So the way we would say it, we would say that the norm of a vector is blah, 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 whatever, some kind of value, right? That's, you can picture it as norm of X, where previously we had min of X, max of X. Norm of X is essentially giving you the norm information. Now, you might be wondering, what is the norm information? Well, the norm function is actually really, really special, right? Um, Before we talk about what it is, let me tell you how we represent it symbolically. So, you can do it this way, or you can do it this way, essentially some kind of function. But in machine learning, well, in mathematics in general, norm is just so special. We give it its own notation, right? Its own notation. And the way we will write, instead of norm of X, we're going to write this, essentially with two double lines around it. And this will represent the concept of norm. Essentially, by doing this, it will tell you the norm. Now, many of us have already seen similar looking functions, like the absolute value. So instead of absolute value function written like this, we very often just write it like this. Okay, so it's actually not an accident that they look so similar to each other. Now, what is happening is that absolute value and norm, they're actually the same thing in that the norm and the absolute value is similar because the absolute value is actually just the norm in one dimension. So if we only have one dimension, then that's just absolute value. But if you have higher dimension, then norm is a more general way of thinking about sizes. So so the way it works, okay? Like let's say we have vector B, which is just dimension 1. Vector C, which is also dimension 1, but they're pointing in different directions, 3 versus minus 3, right? Now, if we take the absolute value of B and C, that's going to give us 3, right? So what's happening is we don't really care about the direction it's pointing. The absolute value just tells us the magnitude, the size of the vector, which is 3, okay? Now, in a higher dimension, the norm tells us, so in 2 dimension now, because 3 is just 1 dimension, 3 and 4, that's 2 dimensions. In higher dimension, the norm tells us the distance from this point to this point. So we can conclude that absolute value tells us the distance here as well, or distance here, right? Now, norm is telling us the distance or the size of a vector at a higher dimension. Higher dimension. Okay? So, how do we extract the length information here? Well, what we are used to is we know that this is 3 and this is 4, so we can calculate the hypotenuse, right? And in a higher mathematical level, we think of them as norms. Okay? Now, There are many, many different types of norms. There's LP norm, L1, L2, L infinity. In fact, there's one called L0, which is not really a norm, but we call it a norm for some reason. Now, so with all these norms, you might be wondering that isn't the distance just from point A to B? Why do we have so many norms? That is, why do we have so many ways of measuring distance? Like, if there's a distance, why don't we just measure this, right? Why are there so many ways? And the reason is because the interpretation of the data. Now, remember, I told you that a vector is only meaningful when we give it some kind of meaning. So if you have a vector that means different things, the concept of distance is actually different. Now, I'll give you an example, okay? So now this is start to finish. So point A to point B, right? Point A, point B. Now, pretend that this green thing is a building. It's just some kind of skyscraper. Now, if you are a bird trying to get from point A to point B, the distance is different than if you're a pedestrian, okay? Now, if you're a bird, you're just going to fly this way. So this is the distance, square root of 2. But if you're a pedestrian who's walking or you're driving a car, you will have to go this way. Therefore, both pedestrian and the bird gets start from the same location and ends at the same location. But the distance they travel is actually different. So a pedestrian, right? A bird will travel this distance, square root of 2, which is hypotenuse. But a pedestrian, you will travel 1 plus 1, which is equal to 2. Okay. Now, yet there's yet another situation where, let's say, if it's 1 and this is 2 here, this is the other corner, and you're not trying to travel that distance. You're just trying to determine the side that's the largest, like max of x. That is yet another distance, which is called the L infinity. So the very first one, which is a bird, that's the one we're used to, the hypotenuse. This is actually the L2 norm. The pedestrian one, where we go like this and here, that is called the L1 norm. And then the last one where you just get the maximum distance, so with the maximum side, that's essentially the L infinity norm, which I just previously said. So this is why there are many different kinds of norms. It depends on the situation and when you were used. Okay. So the way you would write the equation for L1 norm is like this. Okay. So this right here means summation from I to D. So D is the dimension. So let's say you have 3 dimension, 1, 2, 4, right? This is a vector of 3 dimension. So if you want to do the norm of x for norm 1, then you're going to sum is equal to the summation, right, from 1 to d. So d is here 3 dimensions. Okay? So you're going to do this. x1 to the first power plus x2 to the first power plus x3 to the first power. So what is x1 here, which is just 1, plus 2, plus 4. So the norm here is 7. So L1 norm, this is how you calculate L1 norm. See, I write the 1 here to essentially know, so you know which norm it is. Okay? That's how you interpret this. You're summing up every one of them, one at a time, taking the absolute value, and then taking the power of 1. L2 norm is the hypotenuse. Yeah. So let's say we again have 1, 0, 4. So x is equal to this. And now we want to find our 2 norm, right? So you summon all up, right? So the first one will be x1 square, see? Plus x2 square plus x3 square. And the whole thing is square to the 1 over 2 power, which is just taking the square root. So we'll take the square root. And so now we plug the number in, which is 1 square plus 0 square plus 4 square, which is then the L2 norm. Okay? So it's not that hard to calculate these norms. Another one is the L infinity, and that's easy. L infinity norm, you just do the max. 104, which gives us 4. So that one is pretty easy. Okay? In general, these trends follow a very, very specific equation, which is called the LP norm. And you plug in any number, and that will give you the equation. So you plug 1, notice P here and P here. So if you plug 1 here as P, then you plug 1 here and 1 here. So that will give you the manifestation of L1 norm. And if you were to plug the number 2 here, then you notice you plug the 2 here, 2 here. Same as 2 here, 2 here for P. So once you so this is the very general equation. Like it depends on the kind of norm. You pick the norm, plug it into P, and that gives you the equation of the norm. And here's the L infinity norm. You just plug infinity into P here, P here. So when you hear LP norm, that's the general form that gives rise to all the norms. Now you can plug P as 3 or 4. Basically, you can plug P as any number, but for the most part, these 3 are the most commonly seen norms. You're not going to see 3 or 4 very much, like 0.0001% of the time. Like my entire PhD career, I've only seen it once used. That's not one of these norms. So if you learn these ones, that's in general good enough. Okay. Now there is one particular norm that is not a norm, and that is called the L0 norm. 0. So we have 1, 2, and infinity, right? Now we add another one called zero norm. Now the zero norm is a very simple concept. Basically, let's say we have a vector that looks like this, right? Norm 0 of this vector is 3. Why is it? It's because out of 5 elements, 3, 4, 5, 3 of them are not 0. Sorry. Yeah. This. 3 of them. So it gives you the cardinality, L0 norm. And cardinality means out of a vector, you're counting how many of them are not 0. And that's it. It's not that difficult to understand. Okay, so that's L0 norm. Now, for these norms that we've learned, there are actually other names. So L1 norm, depending on the situation, other people call it Manhattan norm because you're imagining you're in the island, New York, Manhattan, and you're traveling this way. Or the taxi, if you're a taxi. So you may see Manhattan norm or taxi norm. It's the same thing as the L1 norm, right? Another one for the L2 norm, its more common name is called the Euclidean norm. Well, in geometry, you call it the hypotenuse, but that's only 2 dimension. Euclidean norm is like any dimension, any dimension. And the last one is called the L infinity norm, also written as this. Now, there are many names. Maximum and supremum norm are two alternative names, and it really makes sense why some people might call it maximum norm or the supremum norm because you're picking the largest number. Uniform norm is actually used quite often as well. So you want to in general have an idea of these names just to know that they're talking about the same thing. And so don't let somebody said, "Oh, uniform norm" to intimidate you. It's really just the L infinity norm. Okay, so now, wow, for each of these vectors, why don't you try calculating the L0, L1, L2, and L infinity norm? Okay, pause the video, give it a second, and give it a try. So you want okay. After you pause the video, I'm going to move on. So we have seen these norms, right? But how do we know if a function is a norm? So we've done a proof previously uh, in the class of how you prove linear function. And with linear functions, we previously showed that it has to satisfy two conditions. First is f of x plus y is equal to f of x plus f of y. And the second one is f of alpha x is equal to alpha f of x. Okay, so the point is when you have a definition of something like linear function or a norm, which is another function, there are certain criteria which you will satisfy. So over here, we're going to have three conditions. The first is called triangle inequality. So, and the second is scaling, third is positive definiteness. Now, I'm not, for the most part, I don't need you guys to know these, but I want you guys to be aware of what they mean so that if you run into it in the future, you have a general idea. Okay. So let's say we have two vectors, um, x and y, right? What the triangle inequality is saying is that if you were to take the summation of them and then the norm, and then compare that with the norm of individual ones, these ones should be bigger. Now, if you look at a triangle, you will see why. So this together is the hypotenuse. And you have x and y. And it's basically saying that the summation of x and y should be longer than the hypotenuse, or at the very least, they should be equal. And we learned that actually in geometry, and that's why it's called the triangle inequality. The only difference is in geometry here is that in geometry, you're looking at it on a plane, but these vectors doesn't have to be in 2 dimension. It could be in like 1 million dimension, right? So triangle inequality is like a very general property that could be in any dimension. And another second condition is called scaling. And what that is saying is that if you have some kind of constant alpha, if you take a vector times alpha and then take the norm, that should be equal to you take the absolute value of alpha and then times the norm itself. So that's what scaling means. So essentially, if it's a norm, it means that you can just move this alpha out and make it positive. That's another property of it. A third property is positive definiteness. It says that a vector x, right, is zero, is equal to zero. IFF. That means if and only if x is equal to zero. So, what does if and only if means in terms of mathematical like notation? Okay. If and only if implies this. Absolute value of a norm, norm of x is equal to 0. When you say if and only if, it means that it automatically implies that x is equal to 0. So if you see that the norm is 0, you know that the x is 0. And it goes other way around. If you see that x is 0, then the norm must also be 0. So that is what if and only if means. So you see this condition and this condition, and you can basically say one imply the other, and vice versa. So these three form the definition of a norm. Now, these the definition of norm is not that important for this class, but I do want you guys to have an idea when you read this, like what it means. Okay, so over here is an example of essentially proving that a particular norm, in this case, I think I use L1 norm. Yeah, I think I use L1 norm. So since since understanding the concept of norm is not that important here, we don't like if you're interested, you should definitely go over this to see if you can prove that a L1 norm is a actually a norm. Okay, but we're not going to go over here. So quick review: we have three kind of norms: one, two, and infinity, as well as 0. So actually four. But again, if we try to use this definition, the triangle inequality scaling positive definite, our zero norm will fail. So it's not going to work. That's why it's not a norm. It doesn't match the definition. But it's very useful query function to extract information, and it acts very similar to a norm. So we just name it our zero norm. Okay, so these are the norms we learned so far, and each norm is useful depending on the meaning of the vector. Now remember, if you're a pedestrian, bird, or if you're just picking the largest value. Okay, and to be a norm, these are the three conditions that needs to be satisfied. Now, when you go on to higher level math, you would need to know how to prove a norm. Basically, when you like need to prove a lot of things, norm will be one of the things that you will need to prove. Now, in terms of how you can find a norm with Python, that's pretty easy. First, you want to import Numpy, like always, and we create a vector. So we've done this already. After you create a vector, you call this command and np.linalg. This stands for linear algebra. And then you call the command norm. At this point, you can put the v in here and say order 1. Order 1 means L1 norm, or order 2, right? Order 2, or order infinity, which over here writes np infinity. Okay, so this is how you calculate the norm. Now remember, this L1 norm is just summation. So 4 plus 3 give you 7. You can see you can automatically calculate the norms very quickly. Okay, now I'm going to change the topic away from norm and talk a little bit about data loading. So when you are working one day or doing something useful, um, when we have large data sets, they're normally stored in files, right? So, and these files are called CSV files. These files are essentially just text files has has the numbers in stored in there, and they're separated by a comma. So, for example, if we have the data here, that is 4 dimension by 3 dimension. Of course, in the real file, it's probably 4 million dimension, and 3 million dimensions. So it's much larger, but let's use a small one for you to get the point. So the file actually looks like this. You have three numbers, right? Separate. You have the numbers separate by commas, and this is the most common way you'll probably see it. And the way you can load the file is you want to import NumPy, and you want to import this thing called gen from text file. Okay. And once you have this command, right, you can call it and load test.csv. So like this right here is test.csv. This is the file. When you open the text file, that's what you see. And you can designate the delimiter, which is comma, right? Comma. After you have done this, then X is now has loaded this data into a matrix. And the matrix, when you print it out, you can see this looks just the same as the data in the file. After this, you can do like different kind of manipulation, x plus 2 times 4, whatever you want to do. Once you do the manipulation, you can say y is equal to this. And then y becomes yet a different matrix. Then you can save y into test2.csv. So np save text allows you to do that. And the delimiter, once again, you want to use comma, and you're saving the y matrix. And the last part here tells you the format. Now, if you write %d, that means they're just integers, bunch of numbers. But sometimes you don't want just numbers. Sometimes you want to have float. So %f for float. And you can control the number of digits. %.3f, that means after the dot, so 0.111. So instead of the entire float, you can just save only up till 3 digits after the dot. Okay, so this is how you can essentially read, manipulate data, and then save the data back out into some kind of file. So here's the final practice of the day. Now, you want to go to the course website and then essentially find the CSV files. They should be in the file folder corresponding to the lecture. So you want to go there, take a look, and then you want to use NumPy and essentially load test A as matrix A, test B as matrix B, C as C, and then load these as vectors. Okay. Once you've loaded them, then you can do various computation on them. Like go through these. So this will allow you to practice what you learned previously, practice loading file, and when you have the chance, what you want to do is maybe export them to some kind of file like test1, for example, CSV, and we'll call this one test2, CSV. So you want to essentially load them, do some kind of manipulation, and see if you can save your result, save the result into some kind of a file. So that's all for today. Yeah, good luck. I will see you guys in the next lecture.